We've covered a lot in this unit. We've looked at parametric and polar functions, and we've talked about things finding the distance around an arc length or finding the area inside polar curves. And so it seems fitting that for the final lesson of this course, actually, it would make sense for us to cover a lot of those things by looking at vector and parametric motion on a curve. So you're going to need your calculator. A lot of what I do is going to be done on the calculator, and I can't unfortunately show a lot of this in this video, but I'll try my best to describe what's happening so you just kind of follow along. So first off, go ahead and enter in that polar function into your calculator, and you may want to actually be in degrees because I'm going to use this trace feature here. And what we're looking for in this problem is the area in the second quadrant that's enclosed by the coordinate axis in the graph. So in other words, I'm really just talking about this region right over here. So in order for me to find the area inside this curve, I'm going to need a couple of things. I'm going to need to know where is this, what is the angle of theta here, and what is the angle of theta at this point over there. And you can see here that my curve doesn't really cleanly seem to intersect my axes at clean integer r values at both points for us to solve algebraically. So this is a case where we can just use the trace feature on our calculator. So take a moment and try that. Well, hopefully you found that this is going to happen here at pi over 2 radians or 90 degrees. And this is going to be at pi radians, okay, or 180 degrees. Well, now that we know those bounds, that allows us to find the area of this region pretty easily. We can say that the area is 1/2 the integral from pi over 2 to pi, and our polar function 2 theta, let me just move this over, 2 theta plus cosine of theta, that entire function squared d theta. So went ahead and I set up my area integral there, and we get approximately 13.338 as our area there. Okay, now let's move on to part B. So for part B, in that same quadrant from pi over 2 to pi, there's one point P. There's some point P that exists on that polar curve where the x-coordinate is -3. And I know we can kind of roughly estimate where we think that it is, but what we want to do is find the exact angle that corresponds to the point P. And then we want to find the y-coordinate of that point P. So what do we know about point P? Okay, so again, let's just kind of work through this. So point P, what do we know about it? We know that for this point, what we're given is that its x-coordinate is -3. So in other words, if we know that the x equation, let's just write this in, the x equation is r cosine of theta, which means our x equation is our polar function, which we said was 2 theta plus cosine theta, that times cosine theta. When this equation is equal to -3, then that's where the point P is. So I'm going to go ahead and then just write this here. We're going to say -3. So let's move this over here. So when our x equation is equal to -3, that's where our point is. Now, this is kind of challenging to do algebraically, although you can do it. For the sake of time, I'm just going to actually go ahead and find the value of theta in my calculator. And the way we would do that, let me just write this. In our graphing calculator, what we're going to do is we're just going to graph, and we're going to write this as a rectangular equation. We're going to write 2 theta plus cosine theta times cosine theta, that entire function, plus 3. What we're effectively doing is we're just moving that -3 over to the other side. And when we graph, we're going to see basically where does it cross, where it crosses the x-axis. And we see that it will cross the x-axis when theta is between pi over 2 and pi. So there are going to be multiple places where that happens. But what we're concerned with is when theta crosses the axis from pi over 2 to pi within this interval. And that's going to happen at 2.401 radians. Okay. So what we did is we found our x equation and we set it equal to -3, and when we graph it to find the value of theta, we just graphed it in function mode in our calculator. And then we found the angle where it crosses the x-axis between pi over 2 and pi radians. Okay, so now that we know what theta is, the final part is for us to go ahead and find this part. What is the y-coordinate of P? So where is y going to give us that when theta is equal to 2.401. So let's write our y equation. It's r times sine theta. So r sine theta. So again, I move this down. Okay, apologize about that. So we would have 2 theta plus cosine theta, all of that times sine theta. And we're just going to evaluate this function at the theta value we found in the previous step, 2.401. And we should get approximately 2.742. And you can do this a number of ways. You could just go ahead and use a table feature, or you could just evaluate it by plugging in. It's up to you. But what we've just done is we found the angle theta. So the point P is when our angle is equal to 2.401, and we found the y value when x is equal to -3. In other words, P, if we express in terms of its rectangular coordinates, would be -3 comma -2.742. That would be its rectangular coordinate. Okay. All right. Now let's move on to part C. So it says that the particle is traveling along the polar curve so that its position at time t is x of t and y of t, such that d theta dt is equal to 2. Find dy dt at the instant that theta is equal to 2 pi over 3. And then we're going to kind of make sure we understand what our answer means in the context of the problem. Quick note, in my solutions that I have uploaded to Classroom, I have a typo where I wrote dy dt in one of my parts. I accidentally wrote it as dy dt. I meant to write it as dy d theta, but I'll write the correct answer here. Hopefully, we'll see. All right, so since I need to find dy dt, I'm definitely going to need to find dy d theta, okay? So let's start with finding y. We said previously that y was equal to 2 theta plus cosine theta sine theta times sine theta. That means the derivative of this with respect to theta would be the following. We would say 2 minus sine theta. So we're applying some product rule action here. 2 theta plus cosine theta times cosine theta. And let's just clean that up a little bit. We've got 2 sine theta if we are distributing minus sine squared theta plus 2 theta cosine theta plus cosine squared theta. All right, now what do we know about dy dt? Because it's asking us to find dy dt. Well, what do you know about dy dt? Dy dt is equal to dy d theta times d theta dt, right? Because we can see here that if we wanted to, we could just divide these out, right? So that's the idea of that chain rule. The derivative of y with respect to theta times the derivative of theta with respect to t, right? This is, again, if you remember our earlier discussions on derivatives of parametric functions, it's just really applying the chain rule in any sense. So what that means for us is the following. We can say that dy dt at the value when theta is equal to 2 pi over 3 is equal to dy d theta evaluated at, dy d theta, what we just found, this previous step here, evaluated at 2 pi over 3, when theta is equal to 2 pi over 3, all of that times d theta dt, which is equal to 2. So again, all I'm doing right now is I'm multiplying dy d theta. I'm going to evaluate that at theta is equal to 2 pi over 3. Then I'm going to multiply it by d theta dt, which was given to us. That's equal to 2. So let me just kind of highlight just to make sure we understand each part here. So d theta dt. So this is what we found in our previous step. Okay. So if you punch all that into your calculator, you can do all this in your calculator. You wouldn't have to evaluate all this by hand. And we should get approximately negative 1.7246. Okay. Now, what does this mean? What did we just find here? What we're saying is the following, and I'll just write it down here. What we're saying is that at theta is equal to 2 pi over 3, when theta is equal to 2 pi over 3 radians, we see that our y value of the particle, the y value of our particle, is decreasing because it's negative. It's decreasing at a rate of 1.7246. That's what's happening, okay? dy dt is stating that the rate of change of y with respect to t when theta is equal to 2 pi over 3. So in order for us to have answered this, we needed to first find dy d theta. And again, it comes back to our understanding that dy dt is equal to dy d theta times d theta dt. All right, now the last part of this problem here is for the particle in part C that we just found. When theta is equal to 2t for some time t, let's find the position and velocity vectors. And this is going over what we did in our previous lesson. So this is, I'm just going to forewarn you, this is just going to be a lot of chain rule action and just a lot of differentiating algebraically. So first off, in order for me to know what our position vector is in terms of t, we need to know what our position vector is in terms of theta. So S of theta would then be the following. We would say it's 2 theta plus cosine theta. Again, this is our r, our polar function, times cosine of theta. And then this is, again, r, 2 theta plus cosine theta, that times sine theta. Okay? Well, now let's write this in terms of t. And so if I distribute that cosine theta to 2 theta, okay, I can just write this as the following. I would say, well, actually, before I write it in S of t, let's actually just clean that up because I don't want to confuse anyone. So we got 2 theta cosine theta plus cosine squared theta, 2 theta sine theta plus cosine theta sine theta. All I've done so far is just distribute. Now I'm ready to write this position vector in terms of t. So we would have the following. So we're going to write this as 2 times 2t cosine 2t plus cosine squared 2t, and then 2 times 2t sine of 2t plus cosine of 2t and sine of 2t. We haven't even done any differentiating yet, but we've got all that. So you clearly clean that up and you would get the position function, although you could leave it as it is. You might as well clean it up since we're going to need to differentiate this in a moment just to find our velocity vector. But I encourage you to now pause and try to differentiate each one of those components. And what you should get is the following. And I'm going to try my best to fit this all in here. What do we have? We've got 2 cosine of 2t, again, minus sine of 4t, plus 4t sine of 2t. There's our horizontal. And then our vertical is 2 sine of 2t minus sine squared 2t plus 4t cosine of 2t, and I'm not going to be able to fit it after all, plus cosine squared 2t. Okay, so all of that is our velocity vector. There's a lot going on there, but just take your time with it, don't rush, and we can see that the velocity vector is just the derivative of our position vector. So go ahead and try the next couple of problems on the back on your own and check your solutions with Google Classroom. And if you've made it this far, congratulations. You finished everything that we need to know for Calc BC.